From Boyle's law, we learned that volume of a gas is inversely proportional to the pressure of a gas. Charles's and Avogadro's laws show that the volume of a gas is directly proportional to the gas temperature and moles, respectively. A, B, and D are proportionality constants which make these equations true. But let's say we combine these equations, then insert a proportionality constant. We can then multiply both sides by the pressure, so we don't have the term in the denominator. The result is the ideal gas law. Where R is the ideal gas law constant, which is equal to 0.08206 in units of liters times atmospheres per Kelvin times mole. The ideal gas law is interesting since it's completely conceptual. Real gases have intermolecular interactions between the particles of the gas, but for gases at high temperatures and low pressures, we can essentially ignore these interactions. At high temperatures, these gases will be flying right by each other with minimal interactions, and at low pressures, the volume is high, so the spaces between these particles will be high, and thus large distances between the particles and minimal interactions. At temperatures and pressures we experience on Earth and in common labs, the ideal gas law proves to be a good approximation for volumes of gases, with minimal error. There are 0.750 moles of helium in a balloon at 23.0 degrees Celsius and 1.05 atmospheres of pressure. What is the volume of the balloon? First, let's recognize there's no change in the conditions. We only need to find the volume at one point in time. Therefore, I'll use the ideal gas law. I'll divide both sides by the pressure to get the volume by itself on the left side. I'll insert the moles, temperature converted into Kelvin, and the pressure. R is the gas law constant. I'll check the units first. Moles cancel, atmospheres of pressure cancel, and Kelvin cancels. Volume in liters remains. This is a 17.4 liter balloon. A 25.0 liter gas cylinder contains an ideal gas at 19.0 degrees Celsius with a pressure of 9.25 atmospheres. How many moles of gas are in the cylinder? First, we'll recognize there are no changes in the conditions, but rather, we want to find the moles at one point in time. I'll use the ideal gas law. I'll divide both sides by the gas law constant and temperature to get the moles by itself on the right side. N, the number of moles, is equal to the pressure times the volume divided by the gas constant times the temperature in Kelvin. I'll insert the pressure and volume. Then divide by the gas constant and temperature converted into Kelvin. Checking the units, atmospheres cancel, volume cancels, and temperature cancels. Moles in the denominator of a denominator will go to the numerator, and 9.64 moles of gas are present in the cylinder. In earlier videos, I explained Boyle's law, Charles's law, and Avogadro's law. These gas equations are true assuming two variables remain constant. But what if three variables change? For that, let's return to the ideal gas law. Recall that R is the proportionality constant. Let's say we divide both sides by Nt, the moles and the temperature. With Nt canceling on the right, the ideal gas law constant will equal PV over Nt. As you can imagine, if these variables change, the ratio of PV over Nt must still equal R. Now we have what is commonly referred to as the combined gas law. Here's an interesting question that appears in nearly all general chemistry textbooks. There is a 3.0 milliliter air bubble at the bottom of a lake where the pressure is 1.70 atmosphere and the temperature is a cool 6.0 degrees Celsius. The air bubble rises near the surface of the lake where the pressure is 1.0 atmosphere and the temperature is 20.0 degrees Celsius. What is the new volume of the bubble? Let's recognize first that there are changes in three conditions: the pressure, the temperature, and the volume. Since moles is not mentioned, we can assume that moles are constant in the bubble. I'll use the combined gas law. Let's get some data first. The initial and final pressures are given in the problem. The initial and final temperatures are given in the problem. I'll have to convert these to Kelvin by adding 273.15. The initial volume is given in the problem, and I'm looking for the new volume of the bubble. Since moles are constant, I can ignore the mole terms in the combined gas law. I'll multiply both sides by T2 and divide both sides by P2 to get the final volume term by itself. Here's the equation for the final volume. I'll insert my values in each term. Notice the conversion to Kelvin for each temperature. The final volume of the bubble is 5.4 milliliters.